In example 3, we get to apply the first derivative test using table form to analytically determine where this function has intervals of increasing, decreasing, and local extrema. Then we'll verify our results graphically. Okay, so referring to the previous page, we have 5 steps to go through. Our first step is the domain. Sometimes the domain of the function is restricted. This time it's the full domain. So the domain of f of x, since it's a polynomial, is all real numbers. Because it's polynomial. All right, so I've got the domain. Second, what I need is the derivative. I need the derivative to get the critical values. So the derivative f prime of x is 21's derivative is 0 minus 24 times 1 plus 9 times 2 is 18. X to the negative 3 times 1 is 3, x squared. I'm going to just rewrite that to put it in descending order. So that's negative 3x squared plus 18x minus 24. And then I want to set the derivative equal to 0 and find out where it fails to exist. Since this is a polynomial, there are going to be no places where it fails to exist, but I still want to look for them because that's not always the case. So I'll do that one first. Then we'll go back and set it equal to 0. It looks like it's factorable by negative 3. So if I take negative 3 out, we have negative 3 times parentheses x squared minus 6x plus 8 equals 0. And then that's factorable again into negative 3 times x minus 2x minus 4. So we have x equals 2 and x equals 4 as the two critical values. All right, now that we have our two critical values, we're ready to do step 4. Okay, so step 4, we're going to make a table. Okay, so in our table, we need test intervals. I'm going to abbreviate so that everything fits here. I need test intervals. I need test values. Again, look at the previous page for an idea of what I'm making for this table here. I need the sign, so just an abbreviation for this, just plus or minus. I'm just going to put a plus or minus symbol in there. And then I need a statement of increasing or decreasing. So those are going to be the 4 rows of my table. The test intervals partition the domain. So my domain was negative infinity to infinity. So I'm going to go from negative infinity to my lowest critical value, which in this case is 2. So negative infinity to 2. Then I need to go from 2 to 4. Then I need to go from 4 all the way to infinity. So I partition the domain, break it twice, one time for each of the critical values. So with 2 critical values, I made 2 breaks and therefore have 3 intervals. Okay. Now, I'm going to pick a test value, which is any value in this interval. So anything between negative infinity and 2, I'm going to choose 0 because it's going to be easy to plug in. Now, anything between 2 and 4, let's pick 3, and anything between 4 and negative infinity, so I'll go with anything. So 10. Sound good? Just anything. 5 is fine. Okay, 4.1 is fine. It doesn't matter if it's a whole number or not, just something in the interval. Now the sign. We're going to go into the derivative. So in the derivative, I'm going to plug in 0. So 0, 0, negative 24. So I'm just going to put a negative here. It's definitely negative. When I plug in the other values, again, I just want to plug in to the derivative 3. Okay, I don't know what the answer is when I plug in 3 in my head. I just want the sign. So I actually can use the factored form of the derivative to get it a little quicker. So if I plug 3 in to the factored form of the derivative, I have a negative times 3 minus 1 is positive, 3 minus 4 is negative, so a negative and a negative, this one's going to be positive. Or if I plug in 10, I have a negative times 10 minus 2, that's positive, 10 minus 4, that's positive, so a negative times a positive is a negative. Okay. Again, you can just take 3, plug them into your line up here, get a number. I don't care what the number is, I just care what its sign is, whether it's positive or negative. By plugging in 3 and plugging in 10 for the x's, you should get a positive number for 3 and a negative number for 10. Okay, so now my conclusions from that. I have that on the interval negative infinity to 2, the function is decreasing. On the interval 2 to 4, the function is increasing. And on the interval 4 to negative infinity, the function is decreasing. So we can summarize that and say that we are increasing on 2 to 4, and we are decreasing on negative infinity to 2, union 4 to infinity. Okay, so that summary helps us finish step 4, talking about the total intervals of increase, decrease. All right, now we're ready for step 5. And step 5 is classifying those critical values. So we had our 2 critical values up here at 2 and 4. And we just want to classify them as whether they are maxima or minima. So we know that we change from decreasing to increasing, down to up. So at 2, there's going to be a minima. Then we change from increasing to decreasing at 4. So 4 is going to be a maxima. So we can say that there is a min at x equals 2, and there is a max at x equals 4. Now, both of these are local extrema. They are not absolute extrema. Sometimes when we just write min or just write max, we imply the local part of it. I'll write it in right here. They are local mins and local max. Okay. If I'm talking about absolute, I'm going to have to be specific. Usually if I talk about them in general like that, I'm talking about the local extrema. Okay, and for confirmation, if we look over here at our graph, notice I did not find the full ordered pair, the y value for this. I could have. I was just looking at where they are first of all. If I wanted to find the y value, I could just plug these back into the original function. So on my graph over here, I see that I do have a local minimum at the x value 2, and I do have a local maximum at the x value 4. I can also see that the function is decreasing all the way from negative infinity until 2, and it is decreasing again from 4 to infinity, and then between them it was increasing from 2 to 4. So I know all of those things about the function. So that was verifying it. But I actually could have drawn this graph just from this information without having to know what the y values were. I could have gotten a sketch that looked very similar to this.